Tutorial is about calculating the band diagram for triangular or hexagonal lattice using COMSOL. But before going to COMSOL, we should always know two things. They are the dimensions of the unit cell and the reciprocal lattice vector. And actually, people use these two terms interchangeably, either triangle lattice or hexagonal lattice, because as you see here, if I start by some triangle lattice and start duplicating it with the unit vectors of the unit cell, you'll finally see that I have some sort of hexagonal shape. What's important for us now that the unit cell doesn't need to contain only one cylinder, or it doesn't need to contain inclusion of circular shape. It can contain any number of cylinders or any number of inclusions or arbitrary shapes. For example, in this tutorial, we will take this paper as an example and try to replicate the results. It's called Scheme for Achieving a Topological Photonic Crystal by Using Dielectric Material. And as you see here, this unit cell is quite complicated, but it's still triangular unit cell with primitive unit vectors A1 in the x direction and A2 defined at 60 degrees to the x-axis, so it can be defined in as a naught times half ax plus square root 3 over 2 multiplied by vector ay. And here I take only one unit cell of this triangle with all the inclusions in it. As you see, I have many inclusions. It's not just one cylinder. And according to the description in the paper about the dimension, I start writing all the indices of this unit cell here and the centers of these cylinders. So before starting COMSOL, let's define the Brilliant zone. First, we start by calculating the reciprocal lattice vectors B1 and B2. They are function of the lattice vector A1, A2, and A3. But because this is a 2D photonic crystal, there is no variation in Z, so you can select A3 to be any number multiplied by the unit vector AZ. Eventually, this number will cancel out because, as you see, we always have A3 in the numerator and denominator. Actually, this first one is wrong. This should be A2 multiplied by A3. Sorry for this mistake. So now, after calculating this relation, I write B1 and B2 in the X and Y basis. So B1 will be like this and B2 like this. And K naught here is defined as 4 pi divided by square root 3 over A naught. And then I draw the reciprocal lattice space. As you see here, the reciprocal space is periodic with unit cell period of hexagonal shape. And let's now define the Brilliant zone, which is actually one unit cell of this space. So here's my Brilliant zone. And also I define this irreducible Brilliant zone by the points gamma, M, and K. So any wave vector inside the Brilliant zone or on its edges can be linearly decomposed on the basis of B1 and B2, the reciprocal lattice vector. So I write a general wave vector, K small vector. It should be multiplied by some linear factor alpha multiplied by kp1 plus beta multiplied by kp2. Our role now is to sweep the value of alpha and beta such that they cover the edge of this irreducible Brilliant zone. So I need to know what is the value of alpha and beta. I should put to, for example, go to the point M. but I know from here that the point M is 0.5 B1 plus 0.5 B2, so alpha and beta should be 0.5 and 0.5. But for example, at the middle point here, they will be changed according to the slope and the equation of this line. So for this task, instead of changing these two parameters, alpha and beta, let's do some mapping with a small k, such that when k equal from 0 to 1, I sweep for any wave vector from k to gamma, and when small k equal 1 to 2, I go for any wave vector from gamma to m, and when k small from 2 to 3, I go from m to capital K. So now, instead of changing the parameters of alpha and beta, sorry, this one should be B1 and this one should be B2. So now, instead of changing alpha and beta, I can change k, so I have to write alpha and beta as a function of k according to this relation. So for example, if I put k equal to 0, so I choose this branch here, and I get alpha equal to divided by 3. And from here, when k equal to 0, I get beta equal 1 divided by 3. And as I said, when small k equal to 0, this is my capital K point. And as you see here, it actually has the indices 2 divided by 3 and 1 divided by 3. Now we have the dimensions and reciprocal lattice. Let's start COMSOL. So file new, the weather 2D wave domain. And for the general studies, I choose eigenfrequency. I start by writing a normalized wave vector, so I usually choose a naught 1 meter. In the paper, there's some ratio defined between a naught divided by capital R, and they give this value for this ratio. So now I can write R a naught divided by a naught div R. Let's now write alpha and beta. So here, this is my alpha here. It has actually 3 branches, so I should use this if condition, and when k is smaller than 1 or less than 1, I should have this relation 2 divided by 3 multiplied by 1 minus k. Otherwise, if k less than 2, I should have this relation 0.5 multiplied by k minus 1. Otherwise, it should be this last definition, k plus 1. I will get an error here, and this line will be red because I still didn't define small k, but I will do this after I define beta. So I copy this one here and just modify this parameters according to the relations for the beta as a function of k. This last time minus times 5. Then I define small k and give it initial value of 0. The last thing to do is to define this kx and ky. Kx, ky. So kx should be alpha multiplied by k naught multiplied by square root 3 divided by 2. I still also have to define k naught, and ky is k naught multiplied by beta minus 0.5 times alpha. And as I said, k naught is 4 by divided by square root 3 divided by a naught. I get this actually from here. So now I defined everything, kx and ky corresponding to the Brilliant zone. I have the parameters for the geometry, a naught and r. I still didn't get the dimension of the radius of the cylinder. So the diameter is d, and it's given in the paper to be 2 times r divided by 3. Okay, let's now go to the dimensions and start creating our geometry. I go to geometry, draw, or there is a primitive here, choose this one, to draw the triangle lattice here. Add linear, so I know that the first vertex at 0 and 0. So the x and y should be 0 and 0, and the second one at a naught and 0. So this one a naught and 0. And then add linear. It will give you the initial point for the second line, and the initial point is the final point in the line 1. So I have only to change the last point. And as you see here, it should be 3 divided by 2 a naught square root 3 divided by 2 a naught. And then add linear again. Zero, zero. Actually, what I will do is to create only half of this geometry and then mirror it to the other side because they are symmetric. Now let's go to draw the cylinders. I have the first one with radius of course d divided by 2, as d is the diameter, and the x-axis for it is r, and the y-axis for it is 0. And you see actually here it's half of the cylinder, so for this sector angle I choose 180. I duplicate this one for this second half cylinder, but now the x dimensions is a naught minus r. For this third cylinder, I have the x-axis a naught, x dimension a naught minus half r, and the y-axis is square root 3 divided by 2 multiplied by r. And now I have a complete cylinder, so I return the sector angle to 360. Again, I duplicate this one to get this cylinder. It has dimension a naught plus 0.5 r, and the y-axis is the same, but here I also need it to be only 180 degree, and rotate it by 60 degrees. This last one here is 3 divided by 2 multiplied by naught minus third r, and also this is square root a naught minus now I have to mirror this triangle, so I go to transformation mirror, I select all of these inclusions and point on line of the reflection, which is this point here, and this is square root 3 a naught divided by 2 and for the y axis no, actually this is not a point here has this dimension multiplied by cosine 30, so eventually I get 3 divided by 4, and for the other one I get square root 3 divided by 4, and normal vector to the line of the reflection, so it should be this normal vector. So it have minus 0.5 and square root 3 divided by 2. And then I keep the input objects and I create this one. Now, as a final step, just to make the mesh easier, I can choose union for all of this one and remove this keep interior boundaries, and finally go to add materials. In the paper they said that the cylinder has a permittivity of 11.7 and the surrounding area is air, so I go to this air one and call it dielectric, choose all of this one, and the refractive index is the square root of the permittivity given in the paper, it's 11.7. Now go to boundaries, periodic condition, choose all of these boundaries, okay, periodicity with kx and ky we already defined, and duplicate this one, Just double check because COMSOL have this issue. I don't know why actually. And before creating image, let's go to eigenfrequency and change this to Hertz and start searching for modes from 0 Hertz, and I need 5 modes. Study, I need a parametric sweep for the small k from 0 to 3, and I need 31 point, for example. And go to the mesh and build all. This is quite good for this dielectric structure, so you don't need to make it extremely fine to solve for the out of plane wave vector. So on the paper they solve only for the TM wave. That's why I get this so bad results. Actually, also when I make it TM and solve for out of plane vector, as you see, it solved much faster than the last case. So now I get all the bands I need for any wave vector. You can check with some results from the paper. Actually, you will see similar plots like this one. And what we are interested about is to draw that dispersion diagram. So I go to results, 1D plot group, and from the dataset I choose a parametric solution and right click on this 1D plot group and choose global, and in the global I need to plot the frequency, and in the paper they normalize it by this value, the speed of light multiplied by a naught. And for the axis source data here I choose outer solution, and for the legends I keep it manual and then plot. As you see here, I get exactly the same results in the paper here, but here they only plot for capital K to M, so they only take this portion here from 0 to 2. So actually I have additional data from 2 to 3, and you see that the diagram matches exactly as in the paper. This is for the ratio of A naught divided by R of 3.125. I can also modify to 3 and to 2.9, and I get the same relation here. Yeah, that's it for today. Thank you, and please leave any comment if you have any question.